we're going to introduce the notion of a sequence. What is a sequence? Well, a sequence is just a list of numbers. Here we see one of the most natural sequences, a sequence that every child learns when they're very young. It's the sequence of natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. There are many other sequences that we'll talk about. This sequence you might recognize as the Fibonacci sequence. Let me draw these in here. These are the natural numbers. These are the Fibonacci numbers. The Fibonacci numbers are defined in the following way. Well, let me show you how the Fibonacci numbers are defined. We start with 1 and 1, and then each successive number is the sum of the two previous numbers. So after 1 and 1, we have 2, then 3 is 1 plus 2, 5 is 2 plus 3, 8 is 3 plus 5, etc. The next sequence you'll recognize, it's a sequence of fractions, 1, 1 half, 1/3, 1/4, 1/5, 1/6, 1/7, etc. After that, we have a sequence of reciprocals of powers of 2, 1, 1 half, 1/4, 1/8, etc. Here's another sequence we'll be talking about later, 0, 1 half, 2/3, 3/4, etc. For some reason, here's the Fibonacci sequence again. I'm not sure why that is. But then we'll talk about this sequence as well, -1, 1, -1, 1, -1, 1. You can repeat numbers in a sequence. There's no reason all the numbers have to be different in a sequence. When we talk about a sequence, we would like to have some idea what the terms are for the sequence and some notation to talk about them. So when we talk about a sequence, we'll call a sequence the sequence A sub n in curly brackets like this, or sometimes we'll write the sequence A sub n equals 1 to infinity, indicating we're starting with the term A1. Then the next term is A sub 2, A sub 3, A sub 4, etc. So A1 will always be in the first term of this sequence, A sub n, A2 is the second term, A3 is the third term, etc. So this sequence of natural numbers we can write as the sequence n, indicating here that A sub n is just n. The nth term is the natural number n. Here we'll just give a name to this sequence. We'll call the sequence f sub n, where for the Fibonacci numbers, remember f1 equals 1, f2 equals 1, and for n greater than 2, we have fn plus 1, greater than or equal to 2. Fn plus 1 is just defined as the sum of the two previous terms, f sub n plus f sub n minus 1. So this is what we call a recursive definition for this sequence. Sometimes we'll want an actual formula. I'll get back to the Fibonacci numbers in a minute. Here you see we have a formula for the nth term. This is the sequence 1 over n. The nth term in the sequence is just exactly 1 over n. Take a few seconds, see if you can guess what the nth term of the sequence is, of this next sequence is. These are powers of 2, but be careful where we start. 1 is 1 over 2 to the 0th power. 1 half is 1 over 2 to the first power, etc. So we have a bit of a shift in the index. So the nth term in the sequence is 1 over 2 to the n minus 1. So the third term is 1 over 2 squared. That's 1/4. The fourth term is 1 over 2 cubed, etc. In this sequence, again, you might be able to guess the pattern. The first term is 0, the second term is 1 half, the third term is 2/3, etc. I'll give you a few seconds, try to guess a formula for the nth term of this sequence. One way to help is you'll notice, ignoring the first term for a minute, that for each other term you can write as a fraction where the denominator is just n, and the numerator is 1 less, n minus 1. And you'll see this formula, of course, works for the first term as well. So this is a sequence. We'll write it as the sequence n minus 1 over n, which tells you that the nth term of the sequence is exactly this number. Of course, you could write n minus 1 over n as 1 minus 1 over n, which will be of interest. Here, for some reason, I have the Fibonacci sequence again. A mistake in the slides. Look at this last sequence. Is there a simple way to write down a formula for the nth term? Well, each time you multiply the previous one by minus 1. So you switch from minus 1 to plus 1, etc. If I just take minus 1 and raise it to the nth power, you see when n equals 1, we have minus 1. When n equals 2, we have 1. When n equals 3, it's to minus 1, etc. So this would be the sequence, minus 1 to the n. Of course, there are many different ways you could write a formula for this sequence. Let me show you one of my favorites. If we write cosine of pi times n, when n equals 1, we have cosine of pi, which is negative 1. When n equals 2, we have cosine of 2 pi, which is 1. When n equals 3, cosine of 3 pi is negative 1, etc. So there are many different formulas, but they all give you the exact same things. Try to think of other formulas for that same sequence. So let's go back to the Fibonacci numbers, which are fun for now. Is there a simple formula? This is a recursive description. Is there a simple formula for the nth term of the Fibonacci sequence? And I'll tell you there is, but it's a very surprising one. And if you've never seen this, you'll probably be very surprised what the formula is. I'll just tell it to you, but don't worry, there'll be nothing later in this course which will require you to know this. You can write f sub n, the nth Fibonacci number, as exactly 1 over root 5 times the number 1 plus root 5 over 2 raised to the nth power minus 1 minus root 5 over 2 raised to the nth power. And of course, we need this in brackets here. So the 1 over root 5 is multiplied by the whole thing. Now that might look horribly strange, but try to compute that. Try to look to see what happens with this formula when n equals 1, and you'll see you get exactly 1, the first Fibonacci number. When you try that with n equals 2, you'll get 1 again. Use a calculator and try that for n equals, say, 6. The sixth Fibonacci number is 8. And try to compute this when n equals 6. And you'll actually see that you get exactly 8. Now, as I said, we're not going to be too interested in sequences like the Fibonacci sequence for chapter 11 here in the course for Calc 3, because the main thing we'll be interested in when it concerns sequences is the idea of convergence of a sequence. So let me talk about what we mean by convergence. When we have a sequence, we can ask, what is the limit as n goes to infinity of the sequence? What does it mean to say the limit as n approaches infinity of a sequence is L? Here by L, I mean some real number. This is just other notation to say the same thing. When I write a sub n approaches L, I'll read that as approaches. It's just a right arrow, but we read that as a sub n approaches L will mean the same as the limit as n approaches infinity of a sub n equals L. And sometimes we can write that same thing by saying the sequence a sub n approaches L. Well, what that will mean is that the terms in the sequence, the a sub n's, the nth term, gets very close to L when n is big. We can make that a little more precise. How close should the term get? What does it mean when n is big? Well, in order to make this precise, we want to say that this means the terms of the sequence a sub n get and stay arbitrarily close to the number L. And what does arbitrarily close mean? You've probably seen that earlier in Calc 1 or Calc 2. Arbitrarily close means you tell me how close you want, and eventually the terms from the sequence get that close to L, and stay that close to L, meaning all subsequent terms are that close to L. Now, this is kind of an imprecise way of saying things, but it's a good way to think of this idea of a limit, that the terms get and stay as close as you want to the number L. If you want the terms to be within a millionth of L, if this limit statement is true, then eventually they'll get to be within a millionth of L, and from some point on, they'll all stay within a millionth of L. But if you need them to be within a trillionth, you have to go further on in the sequence, but eventually they'll get to be within a trillionth of L and stay that close. Any degree of closeness you want, you can achieve and have all the terms eventually get and stay that close to the number L. There's a way to write this more precisely in mathematics, which we do here. We say that the limit of a as n approaches infinity of a sub n is L, or these are other ways to write it, as I've already said, if for every epsilon greater than 0, we use a Greek epsilon here to denote some small positive number. It has to be a positive number. If for every epsilon greater than 0, there's a corresponding integer, capital N, such that if little n is greater than capital N, then the absolute value of a sub n minus L is less than epsilon. Let me interpret that for you. Epsilon is how close you want the terms a sub n to get to the limit L. And if you tell me how close you demand the terms get, then I claim eventually they should get that close and stay that close. Well, what does eventually mean? Capital N here is when they start to get that close. At some point in the sequence, n is the index. So if you go to any bigger index, the terms are all within the distance epsilon of L. The absolute value of a sub n minus L less than epsilon means the distance between the number a sub n and L is less than epsilon. I say the distance because a sub n could be bigger than L or smaller than L, but if the absolute value of the difference is less than epsilon, we say the distance between those two numbers is less than epsilon. So no matter how close you demand the terms get to the limit L, eventually there's some number capital N such that after that point, for an index little n bigger than that capital N, eventually beyond that point, that critical point, all the terms are close enough. If this definition is satisfied for some real number L, so that the limit as n approaches infinity of a sub n equals L, then we say the sequence converges. So a sequence which converges has some real number as its limit. If no real number works, then we say the sequence diverges. Let's look at a bunch of examples. Here we have the sequence 1 over n. Remember, this is the sequence 1, 1/2, 1/3, 1/4, etc. Is there some number that the terms of this sequence get and stay close to? Well, it should be clear that this sequence has limit 0. If you go out far enough in the sequence, the terms will get arbitrarily close to 0. You want the terms to be within 1/millionth of 0, go out to the millionth term, and beyond that point, all the terms are within 1/millionth of 0. You want them to be within 1/100 millionth of 0, go out past the 100 millionth term, and we're okay. What about this sequence, which we saw before? This is the sequence -1, 1, -1, 1, etc. Is there one number which these terms get close to? And the answer is no. This sequence diverges. Sometimes we would call this a divergent sequence. A sequence which diverges is called divergent. There's no one number that the terms get close to. You might ask, isn't 1 a limit? The terms eventually hit very quickly. They just hit 1, and then they hit 1 again, and they hit 1 again. But remember, to say 1 is the limit, they would have to not just be close to 1, as 1 is as close to 1 as you would want. It's equal to 1. But then the next term is far away from 1. There's no, if you demand that terms all stay within 1/10 of the limit, there's no number which could possibly work. So there can't be any limit for this sequence. What about the natural number sequence, 1, 2, 3, 4, etc.? Is there any one number which this terms in this sequence get close to? Well, it's easy to see these terms get bigger and bigger and bigger without any bound. So there's no one number they get close to. Any number that one term gets close to, it just gets much bigger later on. This sequence diverges. What about this sequence, n minus 1 over n, which we looked at before? That's the sequence 0, 1/2, 2/3, 3/4, etc. Well, I claim that this sequence has limit 1. In other words, I'll use this different notation. The limit as n goes to infinity of n minus 1 over n equals 1. We can tell that because n minus 1 over n here is equal to 1 minus 1 over n. So I claim these terms in these sequence do get and stay really close to 1. How close? Well, the nth term is exactly 1 over n away from 1. So if I want the terms to be within a millionth of 1, again, I can go out to the million and first term, and from there on, all the terms are within a millionth of the number 1. What about a sequence like this, r to the nth power, where r is just some real number? This is the sequence r squared, r cubed, r to the fourth, etc. Well, here the behavior depends on what r is. So let me show you an example. If r equals 1, we have the sequence 1 to the n, which is the sequence 1, 1, 1, 1, etc. What can we say about convergence of this sequence? Well, it converges to 1. All the terms are 1. They're as close as you could possibly want to 1. You want them to be within a millionth of 1? Great, they're already that close. So if r equals 1, the sequence converges. What if r equals a half? Well, the sequence 1/2 to the n, this is similar to the sequence we saw before, but it starts a little differently. 1/2, 1/4, 1/8, etc. It should be pretty clear this approaches 0. The numbers get and stay really close to 0. I should write it like this, 1/2 to the nth power. In fact, if r is between -1 and 1, then it should be pretty clear that the sequence r to the n approaches 0. Because when you take a number whose absolute value is the same as saying the absolute value of r is less than 1, when you take a number whose absolute value is less than 1 and you take higher and higher powers, the number gets smaller and smaller, getting close to 0 very rapidly. If r equals -1, we have the sequence -1 to the n, which we already saw above diverges. And if the absolute value of r is bigger than 1, then what can you say about r to the n? R to the n just gets bigger and bigger and bigger. If r is positive, it gets bigger and bigger and bigger, so the sequence here will diverge. If r is a negative number with absolute value bigger than 1, like -2 or -7, the absolute value of r to the n gets bigger and bigger and bigger, so it alternates in sign from negative to positive to negative to positive, etc. So again, we see that r to the n diverges. So what's our conclusion with all of this? Our conclusion is that this sequence r to the n converges to 0 if the absolute value of r is less than 1, converges to 1 if r equals 1, and it diverges otherwise.